So, this problem, uh, you're watching some TV show, and let's see here. This fish squirts a jet of water from its mouth at 13 feet per second up to a leaf where this moth sits, and it knocks uh, the moth off of the leaf into the stream. Fish grabs it because fishies move great in water and bugs tend not to. So, because you are a devoted engineer and scientist, you decide that you're going to calculate the angle that would shoot at, because it's obviously a conservation of energy problem. So let's give ourselves a little surface of the water business here. We'll just pick some arbitrary angle that. So this speed here, we're told, is 13 feet per second. So there's some angle to the water surface that this fish squirts their little water bullet stream at this leaf. Excuse me. And we're told that this is at a height of 2.5 feet. Okay. So since everything's in feet per second and whatnot, that means that we need to think of little g as 32 feet per second, or feet per second squared. I like the second per second. So it's an energy problem. And so when you do these energy problems, I want you to use energy methods. You could use projectile motion for this. You could set up the triangle. It's going to require a sine function, and then you'll use the quadratic formula or some sort of solver. You could get the right answer with projectile motion stuff, but we've already done that. So we want to use energy to do this because it requires a different kind of thinking, and it's a bit easier, quite honestly. So let's get at it. So initially, there's all this kinetic energy that fish shoots little water stream. And that water has to be lifted against gravity. So there's work done on or by gravity. In this case, it's done on gravity in lifting that water. And so the kinetic energy, we need to think, we're talking about energy to get the water to go up, and then this gravity thing is a down. So there's this verticalness to this energy exchange. And so it's just not simply half mv squared equals mgh. What it is it has to be, the v needs to be the initial speed in the y direction, because the work done by gravity is a force times a distance. So remember, we're talking about a force times a distance. And if we were to write FD cosine theta, which is the formal way that you'd write it, go look it up in the book, that theta, that is what fraction of the force is parallel to the displacement, or vice versa. It really wouldn't matter. And so here it's there's got to be something parallel. Well, this initial velocity, 13 feet per second, that is a rectangular vector. There's some x and y part to it. So since the work done by gravity is a y part, I need the speed to be a y part. And this actually turns out nicely for us, because what this means, besides the fact that the masses drop out, okay, and if I multiply both sides by 2, Okay, so now I get v naught y squared equals 2gh. That's nice. Well, v naught y squared, what is that? Well, that would just be v naught squared times sine theta, or sine squared theta, because v naught y would be v naught sine theta, and that thing squared would be those two factors squared. So now it's not going to be hard to figure this out, because now I got a sine squared theta. So let's just keep going here. Sine squared theta 2gh over v naught squared. Those are all things we know, which means theta would be the inverse sine of the square root, and unsquare that side, 2gh over v naught squared, which are all known things in the problem. And it ends up being the case that theta is roughly 77.4 degrees. And so that's the angle that this fish would have to shoot it. And that's good because that's a pretty steep angle. So hits it, bug falls. As the bug's falling, the fish can not even give him time to react. And so now, maybe the bug gets lucky and shakes the water off and flies away, but probably not. So it's a pretty simple, straightforward energy balance. These two things have to be equal. The exchange, and there's multiple ways we think about this exchange. Usually it's initial and final. And here it was. Initially there was all kinetic energy in the jet of water that the bug shoots. And that water had to be lifted as high as the bug or the leaf was. And so that exchange between two states of the system, which took time to get from one to the other, but energy doesn't care about time. Well, it does. It's just bottled up in the zeroth law theorem part of that. All right. Good old kinetic sculpture problem. So this one could be done by forces. We're going to do it by way of energy. So let's we can just draw the picture, I guess. So there's a pulley, and there is a, let's see, this one that's going to end up being close to the ground. I ended up calling that mass 2, which means this is mass 1. So it's 6 kilograms. And so we, in this problem, 0.5 meters, 2 meters. So now we've drawn a picture of this problem. Let's think about the situation. So again, initial and final conditions of the system. So in our energy balance, I'm going to talk about energy balance. I'm going to require that you do energy pie charts, because they are an efficient and concise way for me to understand what your thinking was, and as opposed to having to write out all the words or explain it verbally. So initially, all the energy in the system is bound up in the gravitational potential that these masses have because they're above ground. And so when I do energy pie charts, I usually don't care about is it actually a 50-50 split? Obviously it's not. The heavier mass is higher off the ground. That's going to be a bigger piece of the pie than the smaller mass that's closer to the ground. But I just want to account for how many, sort of like a system schema, doesn't account for magnitude forces. It just accounts for interactions or the pieces of the puzzle. All right. Now, we know that this 6 kilogram mass, it's going to fall. It will hit the ground, And when it hits the ground, it will no longer have gravitational potential energy, but uh, the other one will. So I know that on the final side of this equation, there's going to be only one gravitational work um, term. And there's going to, both of these blocks will be moving. Of course, we're taking it right up to this point right before they stop moving, that nanosecond, that nanometer right before the 6 kilogram block hits the ground and stops moving. And so I have two kinetic energies. So I could say kinetic 1, kinetic 2, and the work done by gravity for mass 2. This one here. Okay? So these two have to be equal. And now that I've identified two kinds of MGHs on the left, one kind of MGH on the right, and two kinetics over there. So what do we get? So M1G height 1 plus M2G height 2 would have to equal mass 2, because it's going to have a new height 3, which is going to be the sum of the first two. Because if the 6 kilogram mass drops 2 meters, that means the 4 kilogram has to rise 2, adding to the half that was there, so that's going to be 2.5. And then we're going to have 1/2 m1v squared plus 1/2 m2v squared. Now I didn't do v1 and v2 because they have the same speed. They're going different directions, but I don't care about the direction. Energy could care less about the direction unless you're inserting a force, a work term, and you need to make sure that you have the component, the parallel part of that. Otherwise, energy doesn't care about direction. Well, let's see here. If we rearrange this a little bit so we can do the math, we're going to have, let's see, half of those first two masses plus the speed squared. And then we're going to have m1 gh1 plus m2 gh2, whoops, not a plus, a minus m2 gh3. And let's see here. We can multiply everything by that, and that'll kill the 2's. We can divide that away, and that'll mean that my v squared, or I could just go for the square root, I guess, of all that. So it looks like G comes out of there as well. G is common to every term. So 2 times, let's see, this is all metric, so we can go with 9.8. 6 plus 4 down here. Let's see. M1H1, so 6 times 2 plus 4 times half minus 4 times 2.5. Something like that. And so that's going to give us 2.8 meters per second at the speed. We want to know what speed does it hit the floor. If you were to look at page 142, which is in the energy section, you would see for the Atwood machine the same configuration, that in comparing it to the forces approach, we would have 2 times the difference in masses, bigger minus smaller, G times delta Y. And this part right here, that's just acceleration. All right. It's always the acceleration for a classic Atwood. Two weights connected by one string over one pulley. Classic Atwood, the acceleration is always going to be this right here. That's always the acceleration of the Atwood machine. Well, v squared equals 2a delta y. That's just the zeroth law theorem, because this would boil down to v bar dv equals 2a dy. So the zeroth law theorem is just energy again. It's the essence of what energy is as a construct. And that's why the zeroth laws are so powerful, is they force us to do calculus, whether we know calculus or not, or they allow us to get away with it. And they are the essence of momentum and energy. Second zeroth law is the essence of momentum. Zeroth law theorem is the essence of energy. And so we could have gone straight to that, and you'd still get 2.8 out of that. But I need to see this pie chart business and setting up your energy balances when it gets to the test. And so that'll be soon to a testing center near you, online. All right. Next problem. You're driving uphill, driving your car uphill. You brake to a stop. Takes 100 feet of braking. Cop says you were exceeding 30. I guess we're going to find that out. Kinetic friction, since it's moving, 0.6. And so will you fight this in court? Okay, so we got to figure out, is this correct? Did the cop make a mistake or not? And by the way, police do have kind of a workbook or a template they use where, given this length, like a skid mark or various and sundry things, they are able to compute these things with limited information, and they don't have to go through all this physics stuff. And so we can call this length, so D will be this 100 feet of skidding. And so we don't know where on the hill, just 100 feet on this incline, friction was doing work against the car. The force of friction over that distance, bringing the car to a stop. Okay? And this is the height. There's going to be, even if you're coming to a stop, as you're going up a hill, you're going to change your vertical height, which means you're going to change your gravitational energy. We weren't given the height, but we were given the length and the angle, or an angle. So we know that the height of this hill will just be d sine theta. So we can bypass that. Now, we do need to know, either we know that the portion of mass that's associated, or the portion of weight that's associated with the friction force or the normal force, we could just know that that's going to be an mg cosine theta because of our prior work with inclined planes, because you know the weight of the car is straight down, but since we're on an inclined plane, we have a different kind of situation. So this normal force here and this mg cosine, the apparent weight, because we've tilted the system, all right? And so that means the normal force will equal mg cosine theta. So we have that little bit of kind of old news that we either need to know from prior experience or be able to develop it, because it's going to be material to our cause here. So initially, it's all kinetic energy. But by the time the car comes to the stop, there's been work done by friction to bring it to a stop, and we've worked against gravity. We've worked on gravity. We've increased the gravitational potential at the same time we were decreasing the kinetic energy by way of friction. Okay, and the height of the hill was also helping take away that kinetic energy. So this is our energy balance, the initial and the final. All right. And so that means I'm going to have my 1/2 mv squared will equal the work done by friction. Well, that's going to be Fd, if you will, to put it simply. And work done by gravity would be mgh. Now, 1/2 mv squared, so friction is mu n, but the normal force is going to be mg cosine theta, so I'll put that d in between there. mg, but h, I don't know h, but I do know d, and I do know theta, so d sine theta. All right, and so we can do all that. Notice that, let's see, GD is common to both of these things, so we can, and M drops out. M is common to every term. So that means that my V, which I can square root everything since that was V squared, would be 2GD, that's all the common terms. That's a terrible mu. Mu cosine theta plus sine theta. And so again, mu is a fraction, pure number. The trig functions are a fraction. So this sum of fractions is telling us the fraction of this 2GD, which is sort of a it's acceleration times distance, but it's G is dealing with a force per unit mass, a particular gravitational force. So it's sort of that underneath the hood of this square root is this force-y kind of thing. I'm being a little loose there. And so let's see, 2 times 9.8 times, well, not 9, well, if you use 9.8, you got to convert the 100 feet. So that would be 30.5 meters roughly. 0.6 cosine 10, yes, plus sine 10. And so V would be about 21.4 meters per second, which is 47.8 miles per hour, to get it back in there. So you could have done it all in units. You're going to have to convert feet per second to miles per hour to make the judgment. Again, I recommend figure out how your calculator does it for you. Most of these nice ones have converters. I have a calculator app that does it too. Google will do it for you. Or you can do it manually. So it looks like you don't want to fight the ticket. And you could, if the cop made a mistake with the workbook or whatever, then you might figure that out. Not many people would, but you being future engineers and scientists, you would have that skill set. And so they might just tear up the ticket just so you'll stop talking about the physics, because lots of people get wet by that. All right, this problem is going to be on the celebration of knowledge. I will suggest, though, that you make a good model of it. And this sort of, it is an inclined plane problem with an energy exchange. And you have more than one energy at the top, and you have more than one energy at the bottom. I'll leave it at that. But this is a relatively simple problem. It's no more or less difficult than the ones that preceded it. Doesn't require any, well, you need to understand the force interactions with friction, so you have the right sort of component there. And so everything that is required for this problem, you've done on other problems. The same is true for this problem. So this one's also on the pending celebration of knowledge. This one's much simpler than the snow ski problem. All right. Okay. So this is kind of probably seems a little silly because basically you're going to put a big spring cushion at the bottom of a hill in case a car loses control on ice and you want to safely stop the car. I've never seen one of these. I doubt I ever will. This sort of thing you might be used in, say, an Amazon or FedEx facility so that they don't break things. But normally if you've ever taken the trip to, say, to Flagstaff, you've seen some little off ramps that are just gravel. And so you'll be going down a hill, but the off ramp goes up. Well, that's using the friction of going into gravel and increasing gravitational potential. And traffic engineers estimate, okay, the fastest that anybody would be coming down this section of road would be, say 90 miles an hour or something like that. And so if they hit the gravel at 90 miles per hour, what angle hill, what kind of gravel or the friction that comes with that, we want to optimize that so that we don't slow them down immediately, but we also don't want them to get to the end of the ramp and then fall down the cliff. All right, so they make these primarily for semi-trucks, because if you lose those brakes, which are hydraulic, then you're going to be moving fast. And so they want to be able to get those big old things off the road so they don't crush cars and whatnot, or knock them off into the abyss. All right, so here's this system, and we're supposed to just basically, all we're going to do is calculate the spring constant in terms of dl and theta. So we won't actually, in this example, find a particular spring constant. You'll need to do that in other things. We're just going to kind of set up the problem. So, here's this hill, and at the bottom of the hill is this spring. In fact, I guess it would be more like that. So we're going to smash it some distance d. We're going to we're going to put energy into the spring by smashing it. Let's see. This is going to be L, and that's going to be theta. So we have dl and theta in our picture. All right. This is going to be the height of the ramp, which would just be L sine theta. All right. Because of the trig of it all. All right. So this means that we would have initially what do we have? Well, it's all gravitational potential, because it tells me that the car starts from rest. So there's no no speed, no kinetic energy to deal with. And then at the end of it, still no speed. So kinetic doesn't even show up in this problem. There's no gravitational potential because it's at a zero height, but we did all this work done by a spring. Okay? Or actually what I should say is potential energy in a spring. So that's our energy balance. Initially it's all this gravity stuff, and then finally it's this spring squashed stuff. So what do I have? Generally speaking, I have mgh equals 1/2 kx squared, except h is L sine theta, and x is d squared. So we would just, we want the K, so just solve for K. So 2mg L sine theta over d squared. Super simple. And if we knew the length of that stretch of road, which would inevitably we would, and we knew, what's the relaxed length of the spring. So let's say this thing comes, it has to, for some reason, meet some length requirement of, say, 10 feet or something like that. Okay, if it's got to be 10 feet for any reason, and that's the way these constraints go, there's some other design constraint that forces this spring to be a certain length. Okay, then I need it, this spring of a certain length needs to have this spring constant to function properly. So then it would be a matter of that vendor going, all right, then it needs to be made out of this kind of metal, the windings need to be this thick, etc., etc. Okay, so, but there we go. If we knew all the L's and D's and whatnot and masses of the car, we could compute that pronto. All right. Now, many of you are too young probably to know who Super Dave Osborne is. You might have heard of David Letterman. But Super Dave Osborne, so somebody weighs 170 pounds, shot out of a cannon 40 degrees from horizontal. It's a tube, so the spring constant is 1,822 newtons per meter. So this stunt, big tube cannon with a chair in it. Somebody cranks that spring down, basically loads that spring, which is the seat's connected to. Let him go, he flies. All right. The bottom of the cannon tube is 5 feet above ground. Small seat attached to that. What he sits on. The spring is released. The spring does 9 feet of extension, so that X in there is going to be that. Sides of the 12-foot tube. So, I guess the spring takes up the first 3 feet of that and the chair thing, and so he's 5 feet above the ground when it does that. All right, so an airbag 3 feet thick for Super Dave to land on, with an average retarding force of 2850 newtons. All right, so those are all the givens. A lot of information there. Some of it useful, some of it not as useful, but none of it useless. All right, well, so initially, what do we have? Initially, you have the potential energy, not of gravity, of that spring, and you have some gravitational potential energy due to height above ground. That's all that's there. Put Dave in the chair, crank that spring down, and wait. So he's some number of feet off the ground. That's some gravitational energy, and the spring is wound up with some amount of energy. All right, 9 feet of squished energy, if you will. And this is going to convey to him moving really fast, or it's going to launch him. So initially and finally, our energy balance looks like that from a pie chart perspective. Okay, so we're going to have to get his speed, and then that speed is going to relate to how he hits the mat, if you will. All right, so let's deal with this. 1/2 kx squared for that spring energy, mgh for, we'll call it h1 for his 5 feet off the ground, and half mv squared. We'll call this his initial speed that he has coming out of there. And so we can, again, I'll spare you all the math, or at least the plug and chug all that. So he's going to come barreling out of there at 14.8 meters per second. All right. So now we know something about this stage of the problem. And now we could take a projectile motion approach here. Now that we know his initial speed, we know that this is going to happen. All right. We don't know what the range is, don't even really care. That's why we're going to use the sine function. All right. Half gt squared plus delta h over v naught t. And this allows us to, of course, if you cross multiply, you'll get a quadratic. We've done a bunch of that. And so what this will tell us is I can get a time of flight at 2.1 seconds out of this. There's nothing obvious about this other than we've got to know what his final speed is right before he hits that mat. Okay, so this, we know what to start with. We know how long the flight will be. So now we can say, all right, Vy, okay, that's associated with that delta H, is going to be equal to V naught Y, thing that we we'll have V naught for. So we do the sine theta for all that minus GT. And so this will convey to the final Y speed for this change in height is going to be a minus 10.7 meters per second. And that's good. It needs to be, he was going up at 14 or almost 15, is going to be coming down at nearly 11. So now we know the final speed. And once we know the final speed, now we can just use the zeroth law theorem. All right. And of course, A is just going to be F over M. So I need you to pause there for a second. Those are the same things. That's Newton's second law. I didn't know acceleration, didn't care to know acceleration, but I do need to know the force that's associated with this change in speed, or the impulse momentum exchange here. That's what we're doing. Again, nothing obvious in my opinion, but we know that we have to go through these kinds of motions to get from things we know to things that we want to know. And so we want to know what distance will put all of this force, mass, speed stuff in balance. And so what we're going to get, so some simplifying as I run out of space here. This relationship, so the distance, and this is like the pole vaulting problem, except now it's using energy instead of forces, but we're not really doing this last step, is fundamentally the same thing as what we were just doing in the last couple of weeks. So if you plug and chug all of this, you get 5.1 feet. This is not good, okay? Because 5.1 feet is greater than the 3 feet of airbag, all right, that he is going to land on. So we need to, something's got to change, or this is going to be, Super Dave's going to the hospital. Somebody's going to get sued. Dave Letterman's not going to be happy because somebody got broke on his show. All right. So that's it. Why would we go through those motions? Well, we know to start with energy balance for an energy problem, and energy solutions tend to be easier than force or momentum approaches, usually, not always. And so we get some information. We also need to know, he's going to come out of the cannon at a speed. That means he's going to go, and a speed at an angle. That means he's going to go some distance. And so that takes time. So there's a time of flight piece of this puzzle. And so you want to switch into just a pure modeling gear. What information can I get? Okay, time of flight starts with this speed. That must mean he hits the ground at some other speed. Basic kinematics in red there. And then, all right, now I have two speeds. Acceleration, I don't have that. Oh, well, there's this force issue. I need to get this 2,850 newtons for the airbag. And so this F over M connection, his mass, that force, will be his deceleration. All right? And so the connection, thick enough to stop all right. That was a lousy loop there. Well, it's not going to erase for me. Or undo. It's weird. So that's that connection there, and that's not obvious. And while those are formulas, it's not like there's a formula for solving a word problem. You have to think it through. Know what these things relate to, because the math is simple. It's just algebra. They don't even energy solutions rarely involve calculus, but sometimes they do. So there's that problem. This next one, I do believe, is in fact the next few. There's an extension of the Super Dave problem that's a little bit easier than the first part. And then again, Super Dave just can't give up on it. And this one is 2. However, I will give you a little bit of hint here. So this blob, some mass on some string length L, is going to get lifted by this thing. And there's going to be some angle that it gets lifted, and that means that it had a change in height. And so this change in height is going to require a little bit of trig going there, because the change in height goes from L minus something. And if you are careful, you can figure out what that something would be. I'll leave it at that. This is a super easy problem. It's literally the energy associated with that change in height, which is a gravitational thing. So there's not even an energy balance here. Just want to know how much energy is used in lifting. All right, this one, demo problem, because I don't think you actually have a test problem on this kind of thing, but we've sort of covered orbits, and so so here's the Earth again, all right? And according to this problem, there's going to be this satellite that's going to collect data, and it's going to take this elliptical path. Just pretend that's an elliptical path. There we go. It's better, but not quite as good as I'd like it. And at the low, we're going to have 100-mile orbital height, and at the high, we're going to have 1,000-mile. So in both, it's moving. Okay, so at every stage of the game, there's a speed. Okay, so here, the radius of orbit is at a minimum, speed at a maximum. Same is true up here. And then at this one, R is at a max, speed at a min, at the farthest point out. So our energy balance, it's not, I mean, you could think of it as initial and final, but which two spots, so I would just pick a low and a high orbit, and those would be my initial and final, but really it's high and low. Which one's initial, which one's final is totally arbitrary. And so sometimes energy is just not so much initial and final as it is these two conditions. And in this case, they're extreme conditions, minimum and maximum something or others. In this case, height versus speed. And so when we write our energy balance, okay, we can say that, so for energy, high, low. So for the moving part of this energy, so there's a kinetic energy form of energy, and then there's a gravitational potential energy that's not the MGH kind. So this is one of the things that can get dicey. And sometimes the way that we describe or label them. So gravitational potential energy from a Newton's law of gravity force times distance standpoint. That one's going to be different than this work done on or by gravity MGH thing. So this isn't an MGH kind of energy. So we're going to have, we could say, K high plus UG high has to equal K low plus UG low. Okay, so 1/2 M, let's see, V high squared plus, and this is what's not obvious, this kind of potential energy is by definition negative. And the same would be true over here. And of course, that means I could just drop the parentheses and have a minus sign in those. And I took up a lot of space there. And so what we can do, if we solve for the V low orbit, okay, what we're going to get just in the algebra will be the V high squared plus 2 GM, because the little mass, hopefully you notice, drops out of every term. And then we're going to have a 1 over R low minus 1 over R high. Okay? And what this ends up being is a ridiculous speed. 67,000 meters per second, which is, it's like 150,000 miles an hour, something like that, 140, 150,000 miles an hour, which is crazy. Of course, we totally ignored the work done by friction, air friction, which would have been a third term on both sides of these equations. So more air friction at the low orbit than at the high. At the high orbit, essentially none probably. And so that would make a huge difference in the final outcome for the speed. And of course we ignored that. I don't think we have many things going 150,000 miles an hour. I want to say 30,000 is about the max. And so the estimate, probably not correct, or we're missing this factor of air drag. So I wanted to have an example of this energy consideration with something that we've modeled a couple of ways now. We've made the Python do the orbits, and we've had a little bit of force interaction math associated with this. So this sort of thing would be what would go into a more advanced, somebody's considering this with a lot more factors, like several more factors like air drag and other things. All right. Some of you might get to do that sort of stuff in the future. All right, this one's going to be on the celebration, and this will be a lot like the car spring thing, except this is going to be flat. It'll be like the Navy, the other problem. So this is essentially another repeat of a former test problem that's related to the other ones. All right, this one. So, ice skater comes down a ramp, does a loop-de-loop. You want to make sure she doesn't fall off the top of the loop-de-loop. So, I'm going to attempt to draw a perfect loop-de-loop, almost. All right, that'll be nice. And so, there's going to be a radius over which this happens, and I'm putting an angle in here for a reason that will become evident later. So at the bottom where she enters the loop-de-loop, she has a velocity for the bottom of the loop. And at the top of the loop, she's going to have a velocity for the top of the loop. All right, we want that velocity at the top of the loop to be big enough so that she doesn't fall off, because that would be bad. And then at all points in between, there's going to be some other velocity tangent to the circular path, which will decrease because it's not like she's on a motorcycle. Gravity's going to start working that speed. So VB is going to be bigger than VT, and VB is going to be bigger than all the speeds between it and VT. Okay, we just want VT to stay large enough after gravity takes a chunk out of it. So this is what we're after. Well, at this spot right here, okay, there is some force considerations to consider, and this is a lot like an inclined plane. So the true weight of the skater will be going straight down. But on that loop, that circular path, at that very point, will be essentially like a ramp. There will be a normal reaction force, okay, that's going to be equal to, or this exchange of force has to be equal to the centripetal. And as you've seen plenty of times, we have an mg cosine theta. So her apparent weight, as soon as she stops being straight up and down vertical relative to the Earth, so instantly the path is feeling a different, less than her true weight, the surface reaction force. All right, and so this force game, the normal force, is now our up force, our center seeking or perpendicular to a circular path, which means that the normal force is center seeking as well, minus the apparent weight relative to the track has to equal this mv squared over r. Okay, so we have this force consideration, or we've modeled this force interaction here, and R is going to be related to the gravitational part of this puzzle because of the way this is set up. So we've drawn a good picture of the situation, which is hopefully communicating some understanding about this interaction and the exchange, helping us arrange for our exchange of energies. We had to consider the force stuff. Hopefully by now you just sort of expect that out of friction or for inclined planes, and this is a curved inclined plane. We still think about it the same way, even obviously though it's not a uniform inclination. So what do we have? Initially, coming into the bottom of this thing, it's all kinetic at this spot right here. And then as the situation progresses, we still have some kinetic at the top. Okay, so there's KB and there's KT. But then there's work done by gravity. Because since it's all icing everything, we're going to assume no friction, and we were not given any information about that. But with ice, we can pretty much put that friction part at zero. Technically, that's not true. And I suspect that if this were a real situation, somebody like you or me would actually consider how friction takes something away. All right? So, okay, how do we move on from here? Good question. So that means 1/2 speed at the bottom squared is going to equal 1/2 mass speed at the top squared, which this VT, by the way, this, oh, I want a different color. VT and V need to be the same, all right? So nothing tells you that explicitly, but hopefully that makes sense why that must be that way. So we'll make that consideration here. Plus mg what? mgh, I don't have an h, and it ends up being the case. It's r times 1 minus cosine theta, which you'll have to figure out why it's that way in a previous problem. But if you just pay attention to the trig of how you have a change in height like this, I've already shown that once, or set you up for that once, but I'm just going to kind of give it away for the sake of time here. Think about what's adjacent here, and it all makes sense. So we have that going for us. So we can get all the V's on one side, everything else on the other. And so what we end up, we can also drop the masses. That's always fun. Interesting that mass always seems to, or frequently, drops out of this game. So a VB squared minus, I'm just going to go with V squared. VT and V need to be the same thing. So the 2 went across, the masses, multiply by 2 to get all that out of there. So 2GR 1 minus cosine theta. All right, that's nice. By the way, theta is going to be 180, okay, because we went halfway around. So it's going to be, there'll be some negatives and whatnot going there. So at the top, what do we get? The weight of the skater has to be mv squared over r, which of course means that at the top, v, or which is vt, has to equal square root of gr. We sort of seen this before, 2gr, gr. It's always part of this kind of circular motion, or some fraction of gr, or multiple of it, be it a bigger than 1 or less than 1. So we have um, that repeating theme, if you will. And so, in the end, all of this uh, works out to be, let's see, so 2GH minus GR equals 4GR. And that means H is 5 halves the radius, which is 37.5 feet. That's a big loop-de-loop. A humongous loop-de-loop. So I'm gonna, well, always goes faster with this group. Yeah, maybe we'll keep going. That'll be nice. So now we're going to switch into Momentumville here. So you're a concerned citizen. You've grown up, you have children, you're on the PTA. Junior high school students in sports programs. 40 kilogram student jumps 1 meter straight up. 80-gram basketball, that may or may not be useful. 30 degrees from horizontal at that speed. Okay, so we have some modeling to do here. So I'm going to write this. This is a generally true statement. The x velocity, a horizontal speed, will always be the initial speed that we were given, namely this one. These are not numbered. I dropped numbering from another document, so go with the pages more than the actual number. It's a good thing I was looking when I saw that. Let me get the chat line in view here. That way I won't miss them in the future. So no, we just, well, yes and no. Yes, there was a 14 in the original document, and I axed it for some reason. But page 14. I think I wanted to keep track of my problem banks, so that's why I did that. I think that makes sense to me. All right, so here's the statement. And so we can, we need to, generally speaking, unless everything is in 2 or 3D vectors and we have a tool that lets us add, subtract, all that stuff, we need to flatten things out in one or more directions. So, but this question, what is the horizontal velocity when he hits the ground? So this gives us a clue that I need to deal with horizontal velocities. Well, this is easy. It'll be 20 meters per second. That's initial speed. Cosine of 30 degrees. That means 17.3 meters per second. That's the initial speed. Now, we conserved energy by saying initial equals final. Every conservation is a balance of initial equals final. And so, or what was the transfer went from here to there, from this system to that system, this person to that ball, this car to that wall, those sorts of interactions. And so the momentum of the basketball has to equal the momentum of the person, if you will. So these two things have to be related. So this is a momentum conservation. So we've not talked about that in a while. You've read about it. You've seen me demo it in other problems with video stuff that you've been forced to do. So we're conserving momentum, basketball to the person. So you could also, I think we have another problem that's a space problem. You know, if you're an astronaut in space and you have a wrench, if you throw the wrench is going to go one direction and you're going to go the other direction. There has to be this exchange of momentum. The wrench will go faster than you because it's a smaller mass, but you will have some sort of speed that you'll pick up in the opposite direction. So throw it well. Same idea here. All right. So momentum, p, little lowercase p, is just a mass times velocity. All right. And the mass of the person times the velocity of the person, which I think we just figured out. And so we need to figure out what's the velocity of the when he hits the ground. And so we solve for mb over mp equals vb. And so this will be in the x direction because of the math we've been doing. So let's see here. The ball was 0.8 kilograms. The person was 40 kilograms. And the speed was, in the x direction, was 17.3 meters per second. And so we get 0.346. At least in the x direction. Might be a little more in the y, but we didn't compute that. We could. We could just go back and repeat all that for the sine part, and we'd go up. Similar kind of situation. Campus Museum, National History. So this hawk, it's a bit more interesting problem. A 1.5 kilogram hawk hovering in the air, dives straight down, speed of 60 kilometers per hour. The goose is a mass of 2.5 kilogram, flying north at 30. So, parallel horizontally at 30, so left or right as far as we're concerned, before it was struck by the hawk and killed instantly. So sad. The animators went to know the velocity and direction of the hawk and dead goose just after the strike. So, for animations, and we've done this where we want realistic speeds, distances. Video games have what they actually call physics engines in them, so that the action is realistic. And realistic takes on a different meaning inside of a video game where things are super powered and whatnot. But you want it to have some sort of connection to reality. And so we impose some physics and then tweak it a little bit in those games. So you've done a physics engine with the Python stuff that we've done, just a totally realistic one, as opposed to other things. So here's the thing, is the mass of we could, let me write this, and then we'll so this look at my notes here. So by m in the x direction, so this is And I'm going to let me write this other part too. Switch up colors. So, hawk versus goose. H for hawk, G for goose. Okay. What do I mean by capital M? So I have two momentum statements, and one in the x direction and one in the y direction. So I'm approaching this problem differently. There's other ways we could go about it. Just pick this one because I could. It's going to be a combined mass in the x. So hawk goes straight down, goose goes straight across, collision happens, and there's a combined mass, and there's going to be, it's not like suddenly the hawk is going to start going horizontal with the goose or straight down. So there's going to be a little bit of both, or at least we presume that would be the case. And it has to be that way given the speeds and the masses. The masses are very close, and one speed is double the other. Okay, and so just a simpler way to approach it in that regard. So the combined mass, so we could say, M equals mg plus mh. So they will stick together, so to speak, when that hawk grabs it. And so we can get from that the two speeds. So mg all right, and so Vx is going to be, when you crunch all those numbers, 18.75 kilometers per hour, and Vy is going to be 22.5 kilometers per hour. All right. So by conserving momentum, and we sort of jump to the gun, so let me go back and say it again. The combined momentum in the x direction, okay, versus the combined momentum in the y direction, okay? Obviously the hawk, whatever momentum the hawk has going straight down, will have to be conserved in the straight down with the total mass of the system. And the same is this way. So I'm conserving momentum along the coordinate system axes, if you will. All right. I don't know. I don't think I approached it this way in the book. And I'm trying to think of a book that does, or which one does. I know some do, some don't. Anyways, it's all in the thinking. So now we have the two speeds, and that's going to be nice. And all we have to do, now that we have an x and y coordinate, if we want to know because basically here's what we have. If we go back to standard vector approach, this means that the vector v has an x component of 18.75 and a y component of 22.5, and these are all kilometers per hour. So it's a vector. Rectangular coordinates, kind of the way we might write them in if we were using Python. So the producers, director, whoever wants to know, they want to know, the animators want to know the velocity, its magnitude and direction of the hawk and dead goose just after the strike. So that's the velocity, but we want to know its magnitude and direction. Well, the magnitude of a vector would just be the Pythagorean identity on that. And so that's going to equal the square root of 18.75 squared plus 22.5 squared, and that's going to be 29.3 kilometers per hour. And then the angle is going to be the inverse tangent of y over x, vy vx, and so that's going to be roughly 50.2 degrees. So we're going to have if it was a polar vector, we'd say 29.3 kilometers per hour at 50.2 degrees. That would be our answer to the animators. And they could make it go that way and then stop at the ground, hopefully. Or put a nice little dent in it. And that'll be that. Let's see here. Let's do another cruise line that sank, and we're going to go get all the stuff out of it or something in this problem. So, summer job, you're hired by a company searching for treasure in the Caribbean. Your employer has discovered captain's logbook of this 40,000-ton luxury liner, the Hedonist, from 1925. And so, going due south at 20 knots. Well, in the fog, struck broadside by the 60,000-ton freighter, traveling west at 10 knots. And so we have a mass, okay, 40,000 ton, and a speed for one ship. We have a mass and a speed for another ship. They're coming at 90 degrees to one another. See, right? Due south. Okay, yeah. So pretty much the same thinking as the bird problem, just we're looking down on it, I guess, from a map perspective. So I went at the bird problem one way. I'm going to go at this one a different way. They're fundamentally the same. So the mass of the Hedonist and the velocity of the Hedonist, the ship, what a party ship, I guess, if they're all hedons on it, and the mass of the Ironside and the velocity of the Ironside is going to be equal to their total mass and their final speed. So it's another energy conservation bit. Here is the initial, or not energy conservation, momentum conservation. Initial momentum, final momentum. Thinking is the same. The equations will be different because they're different physical quantities. All right. So, simple equation, and we know everything but V, I guess, and we could we probably should have a VH. It was going south, I believe, and VI going west. So that's and so that means that there's going to be some sort of, out in this direction. So this would be how if they know where they collided and at what speeds and their masses, they could estimate, where do we, somewhere in here, is going to be where, the treasure is, where the sunken stuff is. All right. So, so that initial statement there, and so we have, and these are momentums, by the way. Each one of these, this is momentum of the Hedon, this is momentum of the Ironside, and this is their total momentum, just P, if you will. All right, so we can, and I'm going to take a kind of a vector notation approach in this one. Generally speaking, well, by definition, in a two-dimensional, this will be the momentum vector, okay, and that has to equal mv. So when you can, you go with vectors, and in fact, you're most likely in the direction that engineers are headed. Other folks, it really wouldn't matter. You probably won't ever do a problem like this if you're not in engineering. You would probably deal with vectors. Your sensor arrays would tell you that sort of thing. So now we can just solve. V is going to be mh vx mi vi, or I could just say mh there, m over their total mass. So the combined momentum, or the two momentums coming together per the total mass that comes out of the end of that, you're going to get, and I suppose we could write it in here, 40,000 times minus 20, because it's going down, and then 60,000 times minus 10, because it's going left, I guess, which way you guys are looking at me, and then this is like 100,000, because some of those two. And nice thing here is you will get a nice vector out of this. This will be in knots, because that's what these units were. They were knots. I forget what the conversion for knots is, but I don't think we don't care about it. So now I know the speed, the magnitude of that speed would be, I think it's 10 if we do the math, but theta inverse tangent of 6/8 or 3/4, I guess, is going to be 36.9 degrees. And so this works out to be, therefore, if you did the magnitude of that vector, you would have 10 knots at 36.9 degrees west of south. And that's the thing you got to be careful of, is what is this, this y over x business. All right. And so that's how we do it. So then it would go 10 knots. How long would it sink? So you could figure they crash, they should start sinking. You know how deep it is there, so you could make good estimates about how fast they would fall in water. That's coming up in fluids, week 11. And so then you could know at what angle to head out and start your looking. So this is how people who do this sort of thing actually do it, based on whatever data they have. Somebody does this sort of thing and estimates, okay, go here and go off in that heading, and it's going to be in the next few miles or whatever. All right. So number 18 is on the celebration, as is number 19, as is 20. So these are all basically repeats of everything we just did in momentum. A little bit of energy in here. So some of these that are in the momentum section are also energy, because this whole thing is a conservation of both. Sometimes it's only energy, sometimes it's only momentum, sometimes it's all the above. All right. What about this one? James Bond movie. He's in love with a bad girl. So let's see here. His latest love interest is 2/3 his weight. When she has skied down a vertical distance of 100 feet, she stops and waits for him captured by the bad guys. Not given a lot of other data. Uh, Standing with her skis pointed downhill while she rests to make as little noise as possible. He starts from rest and just glides, heading right to her. Before they collide, she sees him coming and lets go of her poles. He grabs her, and they both continue downhill. And you want to calculate the maximum possible height that the second hill can be relative to the position where the collision took place. Both Bond and his girlfriend are using top secret frictionless stealth skis developed for the British Secret Service. Okay. Thanks for telling me. All right. So, what is this? So we have to draw a picture of the situation. We have one hill that has a height and another hill that has a lower height. And we're going to do something like this. Okay? So they collide at the bottom here, and that speed lets them get up to the top there. So let's think about the masses. So we have the mass of James Bond. Here we have the mass of his love interest, which was 2/3 of his mass, which means we have at the top the sum of those two masses, which has to be 5/3. 3/3 plus 2/3 is 5/3. So now we have, there's going to be a momentum that Bond has. When he catches up with his girlfriend, they will obtain a new momentum because of additional mass, and then that has to somehow be what speed will allow this collision to get them safely up to the top of the next hill. All right, so and the last few problems are dealing with how momentum and energy are connected. And let's see. All right. Just looking at time here. All right, so we've drawn a nice picture of the problem. So let us begin to, this was 100 feet. Forgot to put that in there. So from an energy perspective, so this is how I'm going to get speed. I'm going to need speed for the momentum exchange. Sort of hopefully know that. So mgh has to equal half mv squared. That has to be true. And so, of course, v would always be 2gh. Okay, and hopefully I better put the right h in there. And so this means, and for this situation, we basically have 80.2 feet per second. So his mass, 32.2 with gravity, feet, and all that jazz. So 80 feet per second. That's moving pretty good. And so now we know his speed coming in that, and that's going to be, I guess, his initial speed at the bottom of the ramp here. So that was energy conservation for the first part, getting to the collision point where now we're going to have a momentum transfer, and then we're going to do an energy balance to get back to that new stuff. So momentum momentum. Yes, make sure I spelled that right. So the momentum that bond had, capital M for bond's mass, initial velocity for what we just obtained from energy. So we're talking about this collision spot here. That will have to equal, because momentum is conserved, the m plus m and their new velocity. Okay, well, we know that new, if we do all this little math here, m over m plus m times v naught, do all the plugging and chugging, and you'll get 48.1 feet per second. So that's good. We would expect that to slow down given that he took on mass. Something's going to get lost in that collision. Or I shouldn't say lost, transferred. Okay, is a better way to frame that. So now we used energy to get bond speed so that we could use that speed for the collision. Collisions mean do momentum conservation. All right, put that in the back of your head. If there's a collision, you're going to conserve momentum. You're probably going to have to conserve energy too. And often you have to conserve momentum so you can use it in the energy equation. So now that we have now we want to get back up to this new hill. How high is this hill going to be, so that this all works out, so that the stunt goes perfectly? Well, we're going to have a m plus m GH. We've got to get that energy back, okay? And that's going to have to be half of m plus m v squared. So I conserve it. The gravity has to equal the kinetic. You could have wrote it the other way. It's perfectly fine. And so this is 5m over 3 GH. And this is going to be 5m over, half of 5m over 3 v squared. And what do we get out of this? That means h is going to be v squared over 2g, which we've done this before. And all of this mass stuff, we didn't really need to do it in this case. And so 36 feet is what it's going to take for this to all work out smooth. But this thing right here that we just used, this is generally true. The masses, unless the mass changed across this somehow, you would never be anything but this. The mass is guaranteed to drop out. And you just get, if we were solving for v, it'd be root 2gh. If we were solving for h, it's v squared over the 2g, etc., etc. So that is a problem that's conservation of energy and momentum, and often you have to do both, especially if there's a collision involved. All right, I think we're doing good. We'll actually finish this. I believe. All right. This is a Tarzan problem so that you can do a George of the Jungle version of that problem. So Tarzan is on some rope of length L that's some height above ground, okay? And he's going to swing and catch Jane at some lower height above ground. And so this, this thing will stop somewhere in the middle. And I think at the bottom, this is where we go from yeah, the mass of Tarzan to uh, yeah. So there's a, what was it? Um, I think I lost track of her mass. Let's see. Tarzan, who has twice her mass. Okay, so uh, Jane comes to grab him. Okay, I had it backwards. Um, uh, Got to be careful here. So here is where he's at, and then obviously an 1M plus 2M is 3M at the top. So Jane saves Tarzan. Had it backwards. Uh, so we have this interesting collection here. So we're going to have Jane's gravitational potential energy is going to go into Jane's kinetic energy. That's just getting us from here to there, to the stage where right before she runs into Tarzan. All right? And so the did a pretty lousy job of, that looks like a big M instead of a little m. So the masses drop out. V, we could, let's probably call this V1 just so that we, so it's going to be square root of 2G big H. Okay. And I think I'm going to leave that out there. So that's the energy part. So V1 will be square root of 2G capital H. So that's the energy piece of the puzzle. The momentum piece of the puzzle, mv1, will equal 3mv2. So here is v1, here will be v2. All right. So in black we conserve energy. In blue we're conserving momentum. So this means v2 is just going to be m over 3mv, or 1/3, just going to be v over 3. And so now we have a way to connect these dots, and so this will allow us to write v2 is 1/3 of root 2gh. And there we go. We pause on that stage 1 of the game, and I really took up a lot of space there. So I'm going to have to be careful in the last part here. So now the energy from, let's see here. So now we're going to go from here to here. So what do I have? I'm going to have half of their combined mass, so I could say 3m, that v squared, and that's going to equal the 3m g little h. All right, and of course 3m drops out, and we want h. And again, looks like we get, but, ouch. we got to put the speed in there first. So 1/2 of 1/3 root 2gh squared equals gh. And of course, that's going to give us 1/9 GH. I have to look at my notes. I'm also scheduled to get new glasses too, so forgive me. But I gotta wait like a month. So this little h height that we were interested in ends up being just 1/9 in the original, because these drop out, and the 2's, I should have a 2 in there, so I have to forgive me for my notes, but it should be h/9. I lost a 2 somewhere in my this this 2 would have come over here, like that. So, and then there's this other 2 that should have been in there. So let me, there we go. So now my 2's drop out. All right. So that's an interesting one, how all those things combine. This one, instead of George of the Jungle, or instead of Tarzan, is George of the Jungle. That's going to be on the celebration. This traffic situation also will be on the celebration. As will this Superman problem will be on the celebration. And the final problem is a classic cannonball problem that involves conserving both energy and momentum in a kind of an important way, and it kind of reveals a secret about explosions that is important to realize, or that a bullet, a projectile that's launched by blowing something up, you get this ability to deal with the momentum, the recoil, and whatnot, and split up that energy in different ways. And so there's 2 parts of this situation. There's the fixed position part of this. So let's see here. The cannon you're testing has a weight of 700 pounds and shoots a 40-pound projectile. So these will be important pieces. In lab tests, held horizontally under rigid support so it cannot move. Okay, so it's fixed position. And the muzzle velocity is 400 meters per second. Okay, so in that fixed position, there's no recoil. So all that energy of exploding, assuming that it doesn't heat it up and all that jazz, we're going to assume that that is the energy that's left in explosion. So the initial energy in this fixed position, all of that energy has to go into the speed of the projectile. All right, and so that means that instead of actually finding that speed, we already know that speed. If it weighs 40 pounds, that's going to be 18.1 kilograms, and it's going to be 400 meters per second. That I switched from pounds to kilograms. And so what we get is 1.45 million joules. Okay, we're going to have to get used to joules as a unit of energy. And so the fixed position situation allows me to compute basically the energy of the explosion. And that's going to be an important piece of this puzzle, not an obvious piece. However, if it's free to recoil, boss asks you to calculate the projectile speed leaving the cannon under regular field conditions when it's allowed to recoil. And so she tells you to go out and fire it using cannon shells which are identical to the laboratory test. Okay, so now in recoil, that's a momentum issue, because now there's that explosion is going to push the mass of the cannonball, which is smaller than the mass of the cannon, or we would 700 pounds versus 40 pounds. And then the rest is going to go that way. So some of the energy of the explosion that we just computed will translate to a change of momentum of the ball and the cannon itself. And so the ball won't go 400 meters per second, because some of that 400 meters per second is going to have to go into recoil. All right? So in the recoil position, configuration, whatever you want to call it, that initial energy, okay, has to go and get split, okay? And in the initial explosion is where all the energy is, and then that's going to go into 1/2 of mass of the cannonball, speed of the cannonball squared, plus 1/2, or I'm sorry, C is for the cannon, B is for the ball. All right, so now the cannon will have some sort of kinetic energy with its mass, and the ball will have some sort of kinetic energy associated with its mass. So we have this thing here, and if we do the kind of the math with them, the mass is like what's half of the mass times the speed squared, we can say, all right, 1.45 times 10 to the 6 joules will equal 158.8 of the speed squared plus 9.1 of the speed squared. And the reason why we're doing this is the next stage is going to be a momentum conservation, where we can put B in terms of C or vice versa. All right, and we want to know the projectile speed leaving the cannon. Okay, and so we can we want to get it to a state where we replace V sub C with something, so that we get an equation only in V sub B. Okay, so because we want the speed of the ball. All right, so momentum. So up here is all energy conservation. And down here, we're going to do momentum. All right, so momentum. The mass of the ball and the velocity of the ball has to be equal and opposite to the mass of the cannon and the velocity of the cannon, which means the velocity of the cannon is going to be the negative ratio of the ball's mass to the cannon's mass times VB. And so when this, this is going to go into there, and therefore C goes away, and it's all in known quantities except for VB, the thing that we want to know. All right, And so that means, I'll switch back to red, I think, here. So 1.45 times 10 to the 6 joules. Could have left that as E sub I, brought it back in later. We're going to have 158.8, and instead of VC squared, we're going to have MB over MC squared. Could leave the negative out because it's just going to get squared away. And then we're going to have VB squared plus 9.1 VB squared. Isn't that nice? All right. And so now the only unknown thing is VB. It's going to be the square root of something since it's squared. So we're going to get this 1.45 times 10 to the 6 joules over I wrote 9.6. I'm not sure. I think I miswrote there. So 389 meters per second. And that makes sense because in the fixed position, it was 400 meters a second. And now that it's allowed to recoil, it's less than that. And not much less than that. You would expect most of it to go into the ball's motion. And so this means if you go back up to this right here, this means that the velocity of the cannon is roughly negative 22.2 meters per second. Usually they're fixed to the ground, so it's going to yank a chain or something like that before it comes to a stop. So curious what I meant by 9.6. I think I just left something off there. So whatever. Oh yeah, I guess it would not be much because of that fraction there. So that is 9.6. Forgot about how this MB over MC squared is taking a humongous chunk out of that 158.8. All right. So that's it. That's a wrap. This will be posted soon. And so you could turn all of this stuff in. We'll probably post the exam, but it'll probably still be something that's due. It'll be like a longer, like a 2-week time frame that it's open for. So